So we continue with the last topic in diffusion, that's the unsteady state diffusion, and we are going to do it for a motionless medium, simply because the convenience of derivation, etc., is there. And then once we consider a motionless media, we will see that there is a one-to-one similarity between what we have learned so far in the context of unsteady state conduction phenomena, and we will see that we can map the unsteady state conduction phenomena to the unsteady state diffusion in motionless media. I want to finish this topic today itself, so we will go through rather quickly, and because we have already seen the solutions in the context of conduction, so therefore much elucidation will not be required. We are going to do here our typical case, that is unsteady state. I have said that it is a 1D scenario we are going to do. We will demonstrate this in Cartesian coordinate. If you remember that I have introduced also in the context of heat conduction equation, unsteady state heat conduction equation, the Slab charts. And the Slab charts, I said that the analytical solution that I had demonstrated for Cartesian coordinate are given in terms of several charts, and similar charts in the are also available for other geometries like spherical as well as cylindrical geometries, which are the consequence of the solution of the governing equation, that is unsteady state term as well as the conduction term. So in the context of conduction, I have specifically shown you heat conduction phenomena. I have specifically shown that the solution for Cartesian coordinate, the same is going to be done here also, and that's why I have selected Cartesian coordinate. But whatever I am going to outline, exactly similar treatment can be extended to spherical as well as cylindrical geometry. Of course, those, because of paucity of time, I will not be able to address. So constant property, and there is no reaction within the body of interest, the medium in which we are trying to investigate the process, and we want to do it in an infinite slab. These are exactly the same problems that we have actually addressed in heat conduction, infinite slab geometry, and the semi-infinite. And in the context of diffusion, these are called thin slab approximation and thick slab approximation. Thick slab, because if the slab is thick, in that case the diffusivity, I have also told you that thermal diffusivity is 2 orders of magnitude larger than the mass diffusivity. So the flow of heat through conduction is going to lead actually the diffusion process. So a thick slab, a diffusing species will see the other end of a thick slab as if it is at infinity, and that's why the semi-infinite geometry is often in the context of diffusion is termed as thick slab geometry, semi-infinite geometry. So these are the two different cases we have dealt, and in the context of infinite slab geometry, if you remember, I have told you, I have shown you that although the derivation is not, I didn't show, as a result of product solution technique, one can derive the solution, and that solution is represented in terms of a infinite series having two different functions. One is an exponential function, the other being a cosine function. Similarly, for the semi-infinite geometry, heat conduction problem, recall whatever I have taught in heat conductions. For semi-infinite geometry, I have shown that the solution can be given in terms of the error function solution, and these are subject to the condition that the boundary concentration or boundary temperature is fixed. So if the boundary condition is changed, in that case the solutions that I have given are already shown in the context of heat transfer, so will not be applicable. So these are the solutions. Infinite series solution as well as error function solutions are for one-dimensional transient diffusion phenomena with specified concentration or specified temperature, which are equivalent scenario or equivalent phenomena. And so therefore, let us look at quickly these two problems we want to do in the next 40-45 minutes and wind up our discussion on unsteady state heat conduction phenomena. So, the slab basically the same type of geometry we are going to. This is the slab and this is the direction in which the diffusion is taking place. Let us say represent this by y. And this is the thickness of the slab, this is 2b, and this is y is equal to 0. So, this is plus A and this is minus A. Okay? So, that is what it is minus A. So, y is equal to plus A minus A represents the boundary of the slab, and this is, I can draw it like this, so make it a little thick, and these are the solid one. And as I said, in the context of heat transfer problem, we dealt this scenario with a fixed temperature boundary condition, and in this case also we are going to deal the scenario, equivalent scenario for a fixed concentration. As I said, and I have been repeating it again and again, how the concentrations are known? The concentrations will be known on the basis of chemical equilibria of the relevant surface reactions that really takes place for transfer of species from the bulk phase to the interface. In the context of heat transfer, we are using a known temperature here at the surface, and that temperature was an empirically determined temperature. So, through some devices we knew the temperature, and that is what we prescribed. And this temperature is a fixed temperature boundary, it is not a time dependent boundary condition that we have applied. So, it is a for all time the temperature was maintained at constant. So, similarly here also we will consider that it is for all time the concentration, surface concentration will be maintained at the same level. So, it is an isothermal scenario as far as mass transfer phenomena is concerned. It is not a simultaneous heat and mass transfer problem. So, if temperature is constant, so it is understood that the equilibrium, state of equilibrium is fixed, hence the surface concentration is fixed. So, we will say constant property, and it is an isothermal problem. Diffusion under isothermal condition. Yesterday, I forgot to mention one term. When I was talking about I will come back to this, but let me, since I remembered that, I should clarify you. Yesterday, if you remember, I was talking about the Kirkendall's effect, where I introduced the concept of drift velocity and also the concept of an interdiffusion coefficient, and that interdiffusion coefficient DAB was represented as dA into xB plus dB into xa. That is, and this I said that we can have the equation, for example, dCA is equal to DAB or we can say that this is and CA also can be represented in terms of, so CC will cancel out, so I can say XA. You could write it in terms of this also. Anything is okay. This diffusion coefficient, now when we are dealing with diffusion coefficient here, so it is an isothermal problem, this diffusion coefficient is a constant. But mind it, this diffusion coefficient, even though the temperature may be constant, is not going to be constant, because by definition, as we see, that the interdiffusion coefficient is a function of concentration, and this concentration itself is a function of the distance. So, therefore, the interdiffusion coefficient, okay, if I have to deal with, for example, a copper, and this is some interface. This is interface, this is copper, and this is nickel. So there's going to be gradient as diffusion starts, there's going to be a difference in concentration. So depending on, so therefore at each point as the unsteady state diffusion is taking place, at each point the concentration is going to be different. Okay, xb is not and xs are not going to be identical here. Okay, they are going to be different. So we will get a position dependent diffusion coefficient. So here this becomes a nonlinear problem. This is not known because this is a function. I want to find out xa as a function of y and t given the value of diffusion coefficient. Okay, that becomes a one equation, one unknown problem. But in this case, also I see that the DAB itself, the interdiffusion coefficient itself, is a function of xb. So this term itself depends on this. So therefore, this becomes a nonlinear equation. The diffusion coefficient values to start with is not known to us. Okay, and it is going to change as a function of time. Okay, because with a function of time, the composition at different locations are going to change. So the DAB value here could be DAB1. On the other hand, here could be DAB3. Okay, at a given instant of time, because the interdiffusion coefficient is a function of. So this is one case where interdiffusion coefficient is a function of composition, and we already know that diffusion coefficient could be given in terms of the Q diffusion by RT activated process, and there we see the temperature difference. So these are the two cases which essentially tells you that in problems the diffusion coefficient itself can depend on composition, and in some other problems it can also depend on temperature also. So the diffusion coefficient basically is a function, as I have indicated, is a function of composition and temperature. So I would say C and T. So therefore they could be interlinked also. So but in this particular problem, because it is a single phase problem, it is just one single material, it could be iron, it could be copper. Okay, there is no interdiffusion, so there is a species which is diffusing through the solid. You can take that this is steel and carbon may be diffusing. Okay, and in this particular case, if we say that it is isothermal, so therefore neither the composition is changing nor the temperature is changing as a function of time. It is of course true that the diffusion coefficient here is, of course, there will be no carbon, so there is the diffusion coefficient will, in this particular case, for example, for a very short time, I would say when carbon does not diffuse here, in that case there is no diffusion, the concept of mass transfer does not arise here. It is here that the diffusion coefficient is going to assume a finite value, and here of course we can have, categorically speaking, there may be a concentration gradient as a function of time. So carbon may be lower here, higher here, and hence also the diffusion coefficient could be a function of concentration. But that complexity we will not consider here. We will treat rather that the diffusion coefficient remains constant. Okay, and so we have the equation now. That equation I can say that if Ci represents the species, and then if you assume that this is constant, then this basically I have taken it y, so this is. So that is the governing equation. And this equation, if you remember what we see, that in the context of heat transfer problem, we have gotten, if you take constant thermal conductivity, then. So if you assume in the heat transfer problem that rho is equal to 1, Cp is equal to 1, and K is equal to D, in that case what happens? T can be interpreted as the concentration itself. Okay? So it is the one and the same. Heat conduction through a pure solid and pure diffusion phenomena in a motionless media are absolutely identical phenomena. So the solution that I had given will be applicable, but let us now complete the statement of the problem, and this is for all time t is greater at initial time t is equal to 0. So for all values of y, and y is equal to, I say plus, this is greater than minus b, and this is smaller than plus b, and then I say that I will not use the suffix I, because I will be used as an initial condition. So I just remove this. So, this represents the concentration of the diffusing species, let it be alpha, it could be I, it could be j, and so on and so forth, because I am going to use suffix as initial concentration as well as original concentration. So, therefore, this could be confusing and I do not want to do. So, C is going to be equal to C0. That is the initial concentration, flat uniform concentration all through, and then at t greater than 0 at y is equal to plus minus b, I have C is equal to C sub s, the surface concentration. And this surface concentration, as I have indicated, is fixed for all time. It is not changing because its temperature is constant. And we can non-dimensionalize this equation, and that non-dimensionalization will give us an equation which we have already said that this we have seen in the context of heat transfer problem. So, in this case theta 1 can define in two ways. For example, we can say Cs minus C0 and C minus C0. This is one possibility, and it is also we can define it at Cs minus C0 and we can say Cs minus C. These are the two possibilities for us. One becomes the mirror replica of the other. If this is the way we define, in that case what happens? Initial concentration becomes is equal to 0. Dimensionless initial concentration will become 0 because I will put at initial what is the value of theta at time t is equal to 0? At time t is equal to 0 for theta will be C0 minus C0, so that is going to be 0. So, similarly theta at the boundary, what it is going to be? Theta at boundary C is equal to Cs. So, Cs minus C0 divided by Cs minus C0, so it is going to be is equal to 1. So, from initial to boundary, this will go like from 0 to 1. On the other hand, if you define it like this, Cs minus C0, in that case what happens? The initial boundary condition becomes 1, dimensionless condition, and the final becomes is equal to 0. So, it is an upside down case. No matter what you want, you can do it either way possible. Okay? And you can see that if I say theta is equal to this, then this becomes actually 1 minus theta. So, there is essentially no difference between the two, only the initial and the boundary conditions are going to be changed. Now, let us say we define theta that initially I want 0 value, very low value, and then finally I want, so my definition of theta is equal to this. And my definition of time is exactly, in the context of heat transfer, we have defined alpha T by L square. So, in this case we will say alpha is d, that is diffusion coefficient, and b is the half slab width. I have cast the problem absolutely analogous to the heat transfer problem, so that there is one-to-one correspondence. I can just copy and paste those solutions from heat transfer here, and that is why I have made this slab not A but 2A to have the same problem as I have discussed in the context of heat transfer. And then I have a dimensionless distance eta which is equal to y by b. So, therefore, the transformed condition becomes, I can say, write with a yellow. So, this becomes tau is equal to 0 for all values of eta minus 1 plus 1, and this becomes is equal to theta becomes is equal to, as you see, theta is this. So, C0 minus C0, so theta becomes is equal to 0. And the boundary conditions, again I write with a yellow chalk, is tau greater than 0, theta is equal to plus minus 1, and C is equal to Cs, and if I put Cs, this becomes is equal to 1. Theta is equal to 1. So, now we can get the solution here, and that solution is going to be theta is equal to C minus C0 divided by Cs minus C0, and this is going to be is equal to 1 minus we'll take it 2 by pi summation, or we can make it 4 by pi, that is better, and then we can say that this is going to be is equal to n is equal to 0, I can say m is equal to 0 to m is equal to infinity, the same summation solution, and then I can say minus 1 raised to the power n m, and this is 2m plus 1. Okay? And then I have the exponential function, and this is equal to minus 2m plus 1 whole square into pi square tau by 4, and then I have the cosine function which is equal to 2n plus 1 pi by 2. And as I said that if I do 1 minus theta, then this is the other definition here, then I 1 and 1 will cancel out. Okay? So, and as you can see here that this will tell us that if you take large time, then what happens is very large time, extremely large time. So, extremely large time solution is what? Extremely large time solution is if I reach the concentration here is 1, dimensionless concentration is 1, dimensionless concentration is 1, then at infinite time everywhere the concentration will be 1. That is the solution of this problem. And you can see here if you put tau, the dimensionless time is of the order of 10 to the power 30, which is a very large number. In that case, this term will vanish. The entire term is going to be vanishing, okay, because this term associated with exponential minus will vanish, and as a result of which C minus C0 will become Cs minus C0. So, therefore, C will be equal to Cs because C0 and Cs from left and right will cancel out, and that itself is the solution, or we will get theta is equal to 1, which I have just now discussed. So, this is consistent. So, I can check that, because I try to write it from my memory, that at least I have goofed up, because at least the minimum is that my boundary conditions must be satisfied by the solution itself. Now, we can have, for example, on the basis of this, the expanded solution, and the expanded solution, because it appears as this is pi square tau square, I think, yes, 2m plus 1 whole square, right, pi square tau, no, that is fine, sorry. So, here for example, if you see that tau, this we have a summation series m is equal to 0, then m is equal to 1. If we try to expand this tau, then we can get pi square by tau by 4 in the first term, because m is going to be 0. In the next case, it is going to be 9 tau divided by 4, and in the next we are going to get 49 by 4, and so on and so forth, okay, because it is 2m plus 1. So, if you take m is equal to 0, then it becomes just pi square tau by 4. If you take m is equal to 2, then it becomes 5 square. So, m is equal to 1, 2 into 1 plus 3, so it is 9 by 4. If you take m is equal to 2, then it is 2 plus 2 into 2, 4, 5, so it is 25 by 4, and so on and so forth. So, and that it is preceded by a negative term. So, we can assume that the first term with m is equal to 0 will give us a reasonably good solution. We really do not have to go beyond that. So, we can say that this we can write as first I will say that we can write 1 minus 4 by pi, and then we can say that this is going to be equal to exponential minus pi square tau by 4 into cosine of pi eta by 2. This is the first term. Then we have exponential minus pi square tau, and this is now 1. So, it is 9 by 4, and this is going to be cosine of n is equal to 1, so it is 3 pi eta by 2, and the next term is going to be exponential. Okay, we got n is equal to 2, and this is going to be 25 by pi squared term 4, and cosine of 5 pi by eta. You can expand it form. And as I said, that large time solution, therefore, the large time solution and in large time solution I would say that because this term is getting amplified, the negative term is getting amplified, and this negative term will tend towards 0. So therefore I can say that this time onwards the terms could be all only we can retain the first term, which is coefficient is 1, and this is 9, 25, and then 49, etc. All subsequent terms can be ignored. So a large time solution, therefore, to make my life simple, I will not write it again, and I can just erase it and then say that this represents my large time solution. That's what it is. Theta large T or large tau. That is the solution. I have just thrown away, and this I will represent approximately equal because I have considered that. We also have, in the context, this large time solution I have not given in the context of heat transfer scenario. Okay? So this, from this you should be able to now, because it is, I just gave you the solution, I think, and I also gave you the expression of flux, but I want to introduce here the large time solution as well as a mean concentration solution, so that you can combine the heat transfer and the mass transfer knowledge, which will allow you to calculate not only the concentration profile, but also the mean concentration, but also the flux at time, at a given time at the surface, and also the large time solution. All these permutations, combinations can be applied not only to mass transfer, but also to the heat transfer phenomena. So you can interchange the derivations and the demonstrations, and then do the calculations, which will be done when we solve a relevant assignment exercise. Now, there is a mean concentration, so we would be maybe interested. Flux expression I am not going to write because the flux is going to have been written. I am going to write for the next. We have concentration which is changing as a function of time, right? So one would be interested to find out that how much of concentration really, how much of carbon has really diffused. Is it 1 kg, it is half kg, it is 2 kg, what? So a mean volume concentration, a volume average concentration is important for us. So we have seen that C is a function of y and t, and now we want to find out that an average C, which is only a function of time, and this will give us, and this basically can be find out that if we do the integration over volume Cyt over the entire volume, if we do, and this is dx dy dz, I will say. It's basically is going to be a triple integral here in 3 different directions, and because only one direction is finite, other directions are infinite, so we can say that this volume actually is equal to L times W0 into 2 times B. That is the volume, in which L represents this directional thickness, W0 represents this directional dimension, and 2B represents this. So the volume is equal to this, and this is going to be equal to, if I integrate, then this will come out to be LW0, and this will cancel out, okay? And then we have integral basically 0 to 2v c yt, and if it's the divided, that's what it is going to be, and this is going to be cancelled. So it is just like a, we have studied time averaging, we have studied area averaging, and this is averaging over the entire volume. Okay? Actually, if you say that this is in numerical form, we say that it is total volume and C into dV, delta V, and summation over the entire volume. So I know the concentration here, concentration multiplied by the volume, so I can discretize the volume into a number of non-overlapping small volume elements, and this represents, delta V represents the volume of such individual volume elements, and if I take the corresponding, so I would say Ci into Vi, and then I is equal to 1 to I is equal to whatever it is you may consider, alpha or beta, and this is the total volume. So that's what is the definition of this. So by integrating this equation, by time averaging this equation, averaging over the entire distance, okay, I will be able to find out. So the moment we average theta, okay, we will find out that with respect to distance, because this is with respect to eta, and this will vary from 0 to 1, okay, or plus 1 to minus 1. So therefore, this term is going to vanish, and only the temperature dependence, because in the process of volume averaging, the dependence of one, we will only get C. So the dependence of y, the resultant expression will show that there is no dependence of distance, because that will fall under integration. When you do space integration, this term will come out, and this term will be integrated between the limit 0 to 1, okay, and then we will get, or sorry, minus 1 to plus 1, and then we will get, the this term here, as you can see here, 2b is there. So when I will integrate this, the minus 1 to plus 1, or I will say 0 to 1, then this t and 2 will cancel out also. So therefore, if we do this, then it is found out, one can do this exercise, this is not a very difficult job. So we will see that C minus, I write it now in a different way, which I define as theta m because of convenience, and now this is Cs minus C0, and that comes out to be 8 divided by pi square, and this is going to be if you remember earlier, the solution was 4 by pi, okay? The pi square, it has come because in the process of integration we will get a coefficient pi outside, okay, and that pi will go into the denominator, 2 will go into the numerator, and from that we get 4 gets multiplied by 2, so we get 8, and then pi gets multiplied by pi, and then we have the m is equal to 0 to m is equal to infinity, and then we see it is the same term that we will write exponential minus 2m plus 1 whole square into pi square. That's what it is. So it is only a function of time. So the mean concentration is only a function of time. The space derivative cosine function has vanished, and from the cosine function the integration has resulted a factor of 2 by pi, and that's how the 4 by pi has. And because I have defined it not Cm by C, so the one term has been taken out. Okay, so this represents the mean concentration, okay, theta mean, and where this is Cm, which is essentially is equal to this is the term. So this will allow us to do all the relevant calculations. So whatever I have taught in the context of heat transfer and mass transfer for diffusion either of mass or of heat through a motionless media, whatever we have learned, there is a one-to-one mapping, and you can get the solution in finite series, you can calculate the heat flux, you can surface heat flux, okay, by differentiating, and you should be able to calculate the mean concentration at any given time. You should be able to calculate that at long time what is the concentration profile, large time what is the concentration profile in the domain, and these all calculations one should be able to find out by simply computing the infinite series. Now, and as I said, that these informations are also going to be available in the form of a corresponding mass transfer Heisler chart. And there, for example, if you look at the, for example, as I said, that if you say now theta versus, so this is our slab, this is our slab, and this is the distance, and suppose and this is the concentration axis, okay, and which I say is a theta axis, and our concentration theta is equal to, suppose theta is equal to 0, this is our horizontal line uniform concentration, and theta is equal to surface, and this is our, and as I have indicated that the steady state solution will be theta is equal to, this is the steady state component. At very small time, you can imagine that this is the kind of solution that we are going to get. We are going to get a symmetrical solution because this is a symmetrical problem. I have talked about it, and then we have as time goes on, that's how the solution is going to approach the steady state value. This is the temperature, the dimensionless concentration variation within the slab geometry, and this is as you go, and these are for different times, which means these are for alpha, because it is one and the same thing, dt by b square. So this may be for dt by b square is equal to 0.01, this may be dt by b square is equal to 0.05, this may be dt by b square is equal to 1, 2, 3, and so on and so forth. For different values, so we have eta is equal to 0 here, and this is eta is equal to -1, and this is eta is equal to +1. So that's how everything varies now. We have converted the equation to a dimensionless forms, and therefore everything now becomes within 0 and 1, nothing goes out, the dimension is between -1 to +1, and theta of course varies 0, and then we have for different values of dimensionless times, these are the curves which come out from the infinite series solution. So we may not do the infinite series solution, okay, if we have to determine only the temperature at any point, we will straightforward refer to this chart, and equivalent chart is going to be available for an infinitely long cylinder. Equivalent charts are available for a sphere, regular sphere. So for a rectangular slab, chart 1, for cylinder, chart 2, and these charts will be given to you when you solve the problems, and you may have already seen actually when you have solved the heat transfer problems, okay, and those similar equivalent charts will be given to you for Cartesian coordinate system, for cylindrical coordinate system, and for spherical coordinate system, and you don't will have to really perform this tedious calculation, for 10 terms or 12 terms. You should be able to refer to these charts and calculate the temperature concentration profile reasonably accurately. Let us start talking about the semi-infinite geometry, and the semi-infinite geometry is the standard error function solution will come, and here also semi-infinite mass transfer in a semi-infinite geometry or thick slab geometry. Mass transfer through a motionless media, and the motionless media under consideration. All other conditions apply, only the geometry is changed, and this geometry is now y is equal to 0 here, and this is y, and the surface concentration. So initial same problem is now, so the equation is now this, Earlier we posed the surface concentration was one dimensional surface concentration. So, we will put this as Cs, this is surface concentration, and we will say that far away from the wall, okay, as y tends to infinity, C is equal to C sub 0. The initial concentration prevails here, and initially, so we have T is equal to 0, C is equal to C0 for all values of so this is our far field concentration as well as the initial concentration, because the diffusing species has not been able to go, it's semi-infinite, it will take millions of years maybe for the diffusion to take place. So, that is not of consideration here. So, the diffusing species in terms of practical time limits is not able to really approach the other end of the finite material. So, therefore, the diffusing species sees the other wall or other end of the domain typically at infinity. And then we have T greater than 0, and that is we have C is equal to Cs, and when we have y is equal to 0 and we have C is equal to Cb or C0, the initial concentration when y tends to infinity. In this case also we can say that the solution of the problem, as I have indicated, that you can do a similarity transformation and then find out by substitution a solution of this. And if you I think a solution, if you look at the thermodynamics textbook by Durkin, then there the derivation is actually outlined. So, he assumes some concentration profile as T to the power half, because the solution is known to us, and based on that the solution is worked out. So, an analytical solution is possible. Okay. Earlier case was infinite series, and in this case we will see an error function solution. And here now theta we can define the same way as C minus Cs minus C0. So, we will say we are not going to non-dimensionalize, but this is what is going to be error function z, and this is going to be x divided by 2 times square root of t. That is the solution, and we have not x, we have y, the error function solution. And you all know, I have already given, I think, the error function of z essentially is 2 square root of pi and then integral 0 to z e to the power minus m square. That's this, I think, the error function definition. Yes. Just check if I have written. Yes. Error function z is equal to. Okay. And this is can be approximated in terms of, for example, a value. If you these values can be just like logarithmic table. One can read really. We have an error function table, so you will be able to read the error function z, and this error function z basically can be approximated by 1 by root over pi, and then it is equal to e to the power minus z square divided by z. So, without referring to table, this is also possible for you to find out. And this complementary error function, ERFC, as I have indicated to you, is essentially the 1 minus error function. That is what is the complementary error function. And these solutions I have given when I discussed, and I also have given you the solution, the flux and the expression of flux. So, you have to, the flux will require the differentiation of error function, and because you have to find out that what is, for the calculation of flux you require this value, right? That is the value that you are going to need. So, dc dy at y is equal to 0. That is what you want to compute. And if you want to compute this here, and you can see that this is going to be minus d dc dy, and this is going to be is equal to, if I write it, Cs minus C0 into 1 minus error function of y divided by 2 times square root d. That is what it is. And so I transpose it, I make it 1 minus error function, that is the right hand side, then I multiply by this, and then once I differentiate this term vanishes, and so C only remains, and that is what it turns out to be, which is equal to, I can write that Cs minus C0, okay, and this minus and this minus is going to make it positive, okay, so minus is there, and this is, I have multiplied it with minus, so this minus and this minus should be cancelled out. So we will say that this is equal to so we need to now differentiate the error function, and this differentiation I have shown you already, and if you do this, then this represents the flux of carbon at y is equal to 0. So, and which is equal to the diffusion flux, which is equal to J. So, J is equal to J at y is equal to 0, and if you do this, then in that case you find this is equal to C0 minus Cs into it's going to be equal to that is what is going to come. So, if you differentiate this differentiation I have already discussed in the context of heat transfer. So, I can give you once again from my notes, if I have it, that if you differentiate error function, then what you really get. So, I do not have it here, but I think I have given it already in the context of heat transfer. If you refer to your old lectures on heat transfer, you will find out how I have, what is the, if you differentiate error function, then what is the result. So, if you do this differentiation, in that case this comes, and a similar expression was also there in the context of, and if you do time averaging, then the time averaging gives us the J average is equal to N average is equal to, if you time average this, then the 2 into Cs, exactly the same expression actually which I have done, and this represents d divided by pi by dE. And this 2 comes because of the integration, okay, t to the power half integral you have to do, and Te is the limit from 0 to t. That is the time over which I want to do the time averaging, and the time averaging definition is 1 by T E 0 to Te, and if you take the flux, which is time dependent flux at y is equal to surface, we are talking of surface flux. So, therefore, this is time average surface flux. These are time average surface flux, and therefore, this is going to be equal to J at y is equal to 0 into dt. So, therefore, that t to the power half will go up, and then t to the power half will become Te to the power half, and that I have a Te here. So, therefore, the final expression will come out to be this. I want to introduce, because I want to finish it, I will take a couple of minutes more, one important parameter which I did not talk, and which essentially tells us, gives us the definition of nominal diffusion coefficient. So, whatever I have done relatively quickly through the unsteady state diffusion problem, because it is the same error function solution which I have discussed in the context of heat transfer in great detail, much longer time I have maintained there. And if you refer to your notes now, you can see there is one-to-one correspondence between what I have taught in the context of heat transfer, and the same applies here in the context of mass transfer. Nothing new I have talked as far as this is concerned, but now I am going to introduce one term which is called the nominal diffusion distance. This parameter, if you now look at the geometry, that how it is going. So, this is our initial concentration C0, and this is the, so the concentration versus distance profile. If you look at it, then the concentration goes something like this. That is what we expect at any given time. That is the concentration. So, it shows the concentration here, carbon has not been able to reach, or the diffusing species, from this surface. Okay, this is the surface at y is equal to 0. Diffusion species has not been able to reach beyond this particular point. So, we can say that there is a penetration distance, and we can also say that there is a nominal diffusion distance. Now, if you take this term, then this is meter square per second multiplied by second. So, it is meter square, square root of meter square is meter. So, that means this term gives you a distance. The distance at which, when, note down this, when initial concentration is 0, so this concentration is suppose 0 for the sake of convenience, then what happens that if I say that this is Cs, for example, so you can, this is, so if this is this much and half of it is what? Half of it is about this much. So, this goes here. So, it is this distance. And so, when the point at which the concentration reaches 50% of the surface concentration is termed as the nominal diffusion distance. Okay? And that nominal diffusion distance is equal to, you can do, because complementary error function ERF of 0.5 is approximately is equal to 0.5. On the other hand, if you take, you want that Cs is equal to, getting, because this curve approaches asymptotically, so it will be difficult for you to get where it is meeting. It approaches almost, asymptotically with this particular horizontal line. So, therefore, you can say that we can assume, most of us assume, or in the textbook it is assumed that wherever this concentration is becomes 10% of the surface concentration, or 0.1 Cs, that distance we call as a penetration distance. You could also take 0.05 also, but customarily we take if the location at which Cs by C is 0.1, okay, or concentration is 0.1 of Cs, that is the distance. That means this is 1. So, I am looking at a concentration which has a value of 0.1. That is what I am trying to say. And if I compare here, does this criteria? No, I go down and I say yes, it is at this location that the concentration is actually only 10% of the surface concentration, and then I can say that this distance now represents my penetration distance, and that penetration distance is given in terms of or 4 times square root dt. So, square root dt represents the nominal diffusion distance, and it is nominal diffusion distance, we say that it is when the point at which the concentration becomes equal to 50% of the initial surface concentration, and the penetration distance is square root of 4 dt, the point location at which the concentration becomes only 10% of the surface concentration. So, we finished our discussion on diffusion, and we will go in the next lecture and discuss in the next lecture about convective mass transfer, which is going to be our last theoretical topic of this particular course.